Hello and welcome back. Well, students, in the last class, we talked about coordination compounds having 6 ligands, and we studied about Sp3d2 hybridization, that is outer orbital complexes, which have more number of unpaired electrons, so they are highly paramagnetic. They are high spin complexes. And D2sp3 hybridization, which generally forms with strong field ligands. In this, the electrons, since electrons they pair, that's why the number of unpaired electrons is lesser. So they are low spin complexes and generally they are diamagnetic and they have a lesser paramagnetic character because the number of unpaired electron is lesser. Today we'll see coordinate compounds containing 4 ligands. So in today's class, first we'll start with hybridization in compounds containing 4 ligands. Well, if I talk about 4 ligands, the two possible hybridization are D2sp3. I'm extremely sorry, not D2sp3. In fact, it is dsp2. So the two possible symmetries in this case are dsp2 and sp3. Again, I'll give you example of that. Suppose I've got a compound like K2 NiCN4. Now in this compound, since it is 2K positive, that means the coordination sphere has got 2 negative charge. That automatically means nickel has got a +2 oxidation state. Now let us draw the electronic configuration of Ni2 positive. Here I have got the 3D subshell. This is 3D. Then I have 4S. Then I have 4P. I need not to draw 4D. This is 4P I've got. The electronic configuration for nickel is scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, and 2 electron in the S. But the 2 electron which were present in the S, nickel has lost those 2 electrons, that's why its oxidation state is +2. Now suppose I've got 4 cyanide ions which are ready to donate its lone pair of electrons. So for that, we had to have 4 empty orbitals. The two possible symmetries are sp3, where you will see 4 empty orbitals, or the other possibility is that this electron will jump here, it will get paired, and the hybridization you will have is dsp2. So in this case, dsp2 will happen because, as I told you earlier, cyanide is a strong field ligand. So if you provide orbitals of high energy, the complex will get a higher energy, it will become unstable. So here the pairing energy is lesser than the repulsion caused by cyanide ion. So pairing will occur. And when pairing will occur, this orbital will become vacant. In that case, you'll have a situation like this, where the electron, the excited electron is here. So in this case, the hybridization is, I'll say the hybridization is dsp2. Since we have used a d subshell of 3, that's why it is inner orbital complex. The number of unpaired electron is lesser in this, that's why it is spin-free complex. Spin-free complex or less paramagnetic. Less paramagnetic. If it is less paramagnetic, either it can be a less paramagnetic or it can be diamagnetic. In dsp2 hybridization, the symmetry is square planar. So here if you have got a Ni2 positive ion, that is connected to 4 cyanide ions like this. Cn negative you'll have here, Cn negative, Cn negative, Cn negative. So here you have got a square planar structure. This is square planar. So in D2sp3 hybridization, it is inner orbital complex because cyanide is a strong field ligand. It will lead to the formation of square planar structure. Second compound I have is K2NiCl4. Same here again, nickel is in +2 oxidation state. It will have the similar electronic configuration. So here I am drawing, it is Ni2 positive. You have 3D, you have 4s, you have 4p, and then you have 4d. We need not to worry about 4d. This is 3d. Again, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel. This is the configuration of Ni2 positive ion because no electron in the S. Now in this case, you have got 4 chloride ions which are ready to donate their lone pair of electrons. Now chloride is a weak field ligand, it does not causes a prominent repulsion. So in that case, the pairing of electron will not take place. In fact, the higher energy P will be provided. So the hybridization, one of the orbital of S and 3 of the orbitals of P will be provided. That means the hybridization will be Sp3. Sp3, as you all know, is tetrahedral. So in this case, here you will have Ni2 positive, 1, 2, 3, 4. These are the chloride ions in tetrahedral arrangement. So this is a tetrahedral arrangement you got. Tetrahedral. This is an outer orbital complex, high spin complex, as you have more number of unpaired electron. It is highly paramagnetic. So this is all about hybridization, Vsepr approach. So according to Vsepr, if we talk about octahedral complexes where we have got 6 ligands, we can have 2 different type of hybridization, that is D2sp3 and Sp3d2, depending on the type of ligands you got. And when you have 4 different four ligands attached to a transition metal atom, you have 2 different type of hybridization, that is dsp2 and sp3. dsp2 again is inner orbital complex, less paramagnetic, spin free. And if we talk about sp3, it is more paramagnetic, more number of unpaired electron, tetrahedral in structure. One thing you have to remember that in octahedral complexes, no matter whether the complex is D2sp3 or sp3d2, the shape is same, that is octahedral. Whereas in compounds having 4 ligands, you will have 2 different type of hybridization, that is dsp2, and in that the shape will be square planar, and sp3 where the shape will be tetrahedral. So this is all about their Vsepr approach. We'll move on to the drawbacks of Vsepr and then CFT later on. But before that, we'll do their isomerism because isomerism is very much based on their Vsepr approach. So now we'll see isomerism. Isomerism in coordination compounds. If we talk about isomerism, I have already taught you this thing in organic chemistry, that isomers are the compounds which have same molecular formula but they have different properties. And if the difference in properties is due to the difference in their structure, we call it structural isomer. And if their structure is also same but their 3-dimensional arrangement is different, we call them stereoisomers. So as far coordination compounds are known, they are known to exhibit both type of isomerism. Coordination compound can exhibit both structural as well as stereoisomerism. So we'll see that. First we'll see their structural isomerism. So first is structural isomerism. Well, as far as structural isomers are concerned, we'll see four different type of isomers in that. That is ionization isomerism. Then we'll see coordination isomerism. Then we'll see linkage isomerism. Linkage isomerism. We'll see solvent. So this is what we are going to do. We are going to do solvent isomers, linkage isomers, coordination isomers, and ionization isomers. So one by one, we'll do them. First, I'll tell you ionization isomerism. The first and the last, they are very much similar. Ionization isomerism. I'm telling you what are ionization isomers. If you want to write down their definition, you can please do that. Ionization isomers are the compounds, coordination compounds, which have the same molecular formula, but they give different products when dissolved in water. Or we can say they are the compounds having same molecular formula, but they give different products on ionization. I give you one example for that. Suppose I've got a compound like CONH3 whole 4 BrCl. And the second compound I've got is CONH3 whole 4 Cl Br. Both the compounds, they have got the same molecular formula. The first one, when dissolved in water or when it undergoes ionization, will give you Cl negative ion, whereas the second one will give you Br negative ion. So first one will give you a test for chloride, whereas the second one will give you a test of bromide. So coordination compounds having same molecular formula but give different products on ionization are known as ionization isomers, and this phenomena is ionization isomerism. Next we'll see second is coordination isomerism. If I talk about coordination isomerism, there's a condition for that both the negative and the positive part of the compound has to be complex. Suppose I got a compound like CONH3 whole 6 CrCN whole 6, and the second compound I've got is CrNH3 whole 6 COCN whole 6. In both these compounds, their molecular formula is same. What's the difference? The difference lies in the coordination sphere surrounding the transition metal atom. In the first one, you'll see that it is cobalt, which has got a coordination sphere of ammonia around it. Whereas in the second one, you'll see it is chromium, which has got a coordination sphere of ammonia around it. So what are coordination isomers? I'm giving you the definition. Coordination isomers are the coordinate compound which have same molecular formula, but they have different coordination sphere around the transition metal atom. In such isomerism, both the positive and the negative part of the compound has to be complex. If both negative and positive part of the compound are not complex, then compound cannot exhibit this type of isomerism. So both positive and negative part of the compound has to be complex. Then only you can see this type of isomerism. So this is what a coordination isomerism is. After this, we'll move on to the next one, that is linkage isomerism. For linkage isomerism, you need to have an ambident ligand. So third one is linkage isomerism. I give you one example for this. Suppose I got a compound like CO, then it is attached to say NH3, Here again you have NH3. Here you have NH3. Here you have NH3. Here again you have NH3. But here you have nitrite group. So the bonding can be ON double bond O, NO2 group. This is the coordination sphere you got. So how we can write it? If I want to express it, I can write it CO NH3 whole 5 ONO, because oxygen is forming bond. Suppose the oxidation number of cobalt in this case is +3. Well, NO2 is always -1. So you'll have 2 positive charge on the coordination sphere. So here you'll have 2 positive charge. Now I'll show you the isomer of this compound. Again, I've got cobalt 1, 2, 3, 4, 5, and 1, 6. NH3, 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 NH3. But this time it is nitrogen which is forming bond. Because in nitride ion, both oxygen and nitrogen, they can form bond. Again, it is 2 positive. If I want to represent it, I'll write CO NH3 whole 5 NO2. So in this case, we'll write it O nitrito, whereas in this case, I'll write it N nitrito. So what are linkage isomers? They are the compounds which have got the same molecular formula, but they differ from each other with respect to the linkage site of an abundant ligand. In order to show this type of isomerism, the compound should have at least one abundant ligand. So in this case, you can see that NO2 is an abundant ligand. You can also have CN, because CN can form bond both from carbon and nitrogen. So in this case, if it is forming a bond with oxygen, then you have to write O nitrito. If it is forming bond with nitrogen, then you have to write N nitrito. Next, we'll move on to the third one, that is hydrate or solvate. Solvate, also known as hydrate. Solvate means solvent, and if the solvent is water, we call it hydrate. It is very similar to ionization. Like say I've got a compound CO H2O whole 5 Cl and Cl. This Cl is negative, this has got a positive charge. The another compound I've got is CO H2O whole 4 Cl2 dot H2O. Well, if you dissolve the first one, you'll not get any water molecule. If you dissolve the first one in the solvent, that is water. If you dissolve the first compound in water, you'll not get any water molecule from it. Whereas in the second one, you'll get one water molecule. That means solvent isomers, they are very similar to ionization isomers. Here also the molecular formula is same, but the product of ionization are different. Anyways, the definition for this type of isomerism is a bit different from that of ionization isomers. What are solvent isomers? They are the isomers, they are the compounds which have the same molecular formula, but they give different number of molecules of solvent when dissolved in a solvent. If solvent is any solvent, we call it solvent isomers. If solvent is water, we call it hydrate isomers. So first one when dissolved in water does not give any water molecule, whereas the second one when dissolved in water gives one water molecule. So they have, even after having the same molecular formula, they are providing different number of water molecules when dissolved in water. So this is what solvent isomerism is. Next, we'll move on to their stereoisomerism. Second is stereoisomerism. We know what stereoisomers are. Stereoisomers are the compounds having same molecular and structural formula, but they have different properties due to the difference in their three-dimensional arrangement. And we have two different type of stereoisomers, that is geometrical isomers and optical isomers. So coordination compound also shows both these type of isomers, and we'll see them. First, I'll talk about their geometrical isomerism. Geometrical isomerism. In both tetrahedral and octahedral complexes. So first is in compounds having 4 ligands. 4 ligands, 4 monodentate ligands, that is this type of compounds. When I talk about this type of compound, you cannot see isomerism in, say, you got a compound like A3X, or you got a compound MAX3, or you got a compound MA4. In these type of compounds, you cannot see geometrical isomerism because their spatial arrangement will be same. You will not have geometrical difference in them. They'll be same. As far my part is concerned here, what by default I'm thinking that you people are quite aware of geometrical isomers. Well, geometrical isomers, again I'm telling you, are the compounds which have like groups in them. If the like groups they are on the same side, we call them cis. If the like group they are on the opposite side, we call them trans. So in this type of arrangement, it is not possible. You don't have like groups which can be on the same side or different side. So overall arrangement, if we talk about, that is all the way same. In this, I'll give you some examples. Like I'll give you example of first, that is MA2 X2 type, where you have 2 different type of ligands. So suppose I have got a compound like CO NH3 NH3 Cl Cl. In this you have got like group on the same side. That's why this form is cis. Likewise, CO 1, 2, 3, 4, Cl, Cl. Like groups, they are on the opposite side. Same goes for NH3 also. So they are trans. You can also have compound like M, A2, X and Y. In such compound, although you have got 2 different type of ligand, that is X and Y, but you have A2. So suppose you have got a compound like CO NH3 NH3 Cl Br, but the 2 NH3 they are on the same side, so this form is cis. Likewise, NH3 NH3 Cl Br, this is trans. You'll not see the position of Cl and Br, you'll stick to the position of NH3. If they are on the same side, it is cis, and if they are on the opposite side, it is trans. So this is how you can see geometrical isomerism in compounds containing 4 ligands, having 4 ligands. Second, we'll see in compounds containing 6 ligands, that is octahedral compounds. So it can be like M, and ligand, if you talk, you can have 6 ligands. So this type of complex you can have. In that you have 2 different type, means 3 different type of complexes. We'll see them one by one. The first I am writing can be M A4 X2. I'll give you one example for this. That is CONH3 whole 4 Cl whole twice. So this is a compound which you got. If I draw the structure of this compound, I can draw it like this. Say CO 1, 2, 3, 4, 5 and 1, 6. NH3, 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 Cl, Cl. The charge on the compound is +1 because cobalt here is in +3 oxidation state. The 2 Cl are negative. Now what you will see, the 2 Cl, they are on the same side. So this form can be termed as cis octahedral. So it is an octahedral complex having cis isomerism. Likewise, I am drawing another compound. The same compound but in different arrangement. You will have Cl, you will have Cl, you will have NH3, you will have NH3, here again you will have NH3, here again you will have NH3. Again +1. But you will see that the two like groups, they are opposite to each other. The two Cl atoms, they are opposite to each other. That's why this is a trans isomer. So in octahedral complex, you got a cis and a trans isomer. I'll give you another example, and that example is say you have got M and A3X3. This is an important one. Please do pay attention towards this one. Suppose I have got a compound CONH3 whole thrice Cl3. This is cobalt I have got. 1, 2, 3, 4, 5 and 1, 6. NH3, NH3, NH3. Cl, Cl, Cl. If you join these NH3, you will see a face of NH3. This is a face formed by NH3. Likewise, if you join these Cl, you will see a face formed by chloride ions. So on one side you got a face of NH3, on the other side you got a face of Cl. That's why this type of isomer is very correctly known as facial or FAC isomer. This is very similar to cis in its properties. Another one I am drawing CO 1, 2, 3, 4, 5 and 1, 6. Cl, 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 NH3, NH3, NH3. The like group, they are on the opposite side. Cl, you can see that it is on the opposite side. That's why it is very similar to trans. But very correctly it is known as meridional or mer isomer. Meridional because the two Cl, they are on the meridian. They are just opposite to each other. That's why it is meridional. So here we have seen this type of isomer. Otherwise, if we talk about cis and trans isomer, we can have another type of compound. I'm writing it here. That is M AA whole twice X2. I'll give you one example to you for that. Suppose I got cobalt, ethylene diamine whole twice Cl2 single positive. For this compound, I'm drawing its isomer. Here I've got cobalt 1, 2, 3, 4, 5 and 1, 6. Ethylene diamine is a bidentate ligand, you know. Then you have Cl, Cl. Again here you have got ethylene diamine. The total positive charge is single positive. I'm drawing another compound for this, another arrangement for this, which can be like this, on which the Cl, they are opposite to each other. Here you have ethylene diamine. Here again you have ethylene diamine. This again has got a +1 charge. My dear students, on the first one you will see that the two Cl, they are very close to each other. They are on the same side. That's why we'll call it cis isomer. And this one is a trans isomer, where the like groups, they are opposite to each other. So it is very similar to the first one. If you have a look at this one, it is very similar to this one, where you got a like group on the same side and like group on the opposite side. But in this case, there was no bidentate ligand, whereas in this case, in the third case, you got a bidentate ligand, that is ethylene diamine. AA means bidentate ligand. So with bidentate ligand also you can have, with monodentate ligand also you can have. This is all about their geometrical isomerism. So geometrical isomerism we can see like this. After this, we'll move on to their optical isomerism. So optical isomerism we'll see in octahedral complexes. Optical isomerism. Well, in organic I taught you that all optical isomers are enantiomers, but all enantiomers are not optically active. In order to show optical isomerism, the compound has to be enantiomer. It has to show enantiomerism. For that, it has to have a chiral center. In octahedral complexes, we come across situations where we see compounds like this. I'll give you first example in octahedral complex. We can have compound like MAA whole thrice. That is 3 moles of bidentate ligand. So for that I can have a compound like COEN whole thrice, 3 positive. Cobalt is in +3 oxidation state. So suppose here I've got cobalt 1, 2, 3, 4, 5 and 1, 6. Here I have ethylene diamine, and here again ethylene diamine, 3 positive. So if this is dextro, I can have a mirror image of this also. That is CO 1, 2, 3, 4, 5 and 1, 6. That is ethylene diamine, and ethylene diamine. You will see that these compounds, they are appearing to be mirror image of each other. They are non-superimposable mirror image of each other. So if this is dextro, the another one is levo. The second type of compound in octahedral complex which can show optical isomerism can be of MAA2 and X2 type. We have already seen this type of compound. Suppose here I have, for that the example which I am giving you is COEN whole twice Cl2, single positive. Again cobalt is in +3 oxidation state. So you have cobalt 1, 2, 3, 4, 5 and 1, 6. Here you have Cl. In this case, ethylene diamine, and it has got a +1 charge on it. You'll have a mirror image of this, CO, Cl, En. So in this one again, you will have +1 charge. If the first one is dextro, the second one is levo. My dear student, you have to remember this thing that this is an octahedral complex which is exhibiting both geometrical as well as optical isomerism. I have already taught you this compound in geometrical isomerism. See, you have seen it here in geometrical. Cis and trans. It is only the cis form of this octahedral complex that can show optical isomerism. It is only the cis form that is showing, not the trans form. So cis form can show dextro and levo type of compound. After this, the other compound which we can have is MAA2. Then you have X2 and Y2. I'm giving you one example for that. That is COEN NH3 whole twice and Cl2. This is the compound I have got. Now I'll draw structure of this compound for you. CO 1, 2, 3, 4, 5 and 1, 6. So Cl, Cl, NH3, NH3 and En. This one has got a +1 charge. Mirror image of this compound, CO 1, 2, 3, 4, 5 and 1, 6. You'll have Cl, you'll have Cl, you'll have ethylene diamine, you'll have NH3 and you'll have NH3. So if the first one is dextro, the second one is levo. So this is all about their optical isomerism. This type of optical isomerism you can see in octahedral complexes. Before winding up with the class, once again a recap of this. We'll move on to their isomerism, right from structural isomerism. They exhibit both structural and stereoisomerism. Ionization isomers are the compounds which have same molecular and structural formula but gives same molecular formula but give different product on ionization. Coordinate isomers have the same molecular formula but they have different coordination sphere around the transition metal atom. Linkage isomers have the same molecular formula but they have different linkage site of an ambident ligand. So for that you need to have an ambident ligand in the compound. Solvent isomers like ionization isomers have same molecular formula but give different molecules of solvent when dissolved in a solvent. In stereoisomers, geometrical isomerism, that is cis and trans. If we talk about compound having 4 ligands, we can have complexes like MA2X2 type, like Cl2NH3 whole twice type. So if the like group they are on the same side, we'll have cis and trans. We can also have compound MA2XY. So we'll put our emphasis on A2. If both the A they are on the same side, it is cis. If both the A they are on the opposite side, it is trans. For compound containing 6 ligands or 6 monodentate or octahedral complexes, we can have complexes Ma4X2, that is NH3 whole 4 Cl2. If the 2 Cl they are on the same side, it is cis. If they are opposite, then it is trans. This form with bidentate ligand also exhibits optical isomerism. We can have another form that is Ma3X3, that is NH3 whole thrice Cl3. They will exhibit facial and meridonial. If the like group they are on the same side, they form face of a type of ligand. So that is facial. If the like ligands they are on the opposite side, they are on the meridian, we call it meridonial. So facial they are very similar to cis and meridonial they are very similar to trans. Then with bidentate ligand we can have Ma2X2, that is cobalt ethylene diamine Cl2. This is the form of an octahedral complex which can also exhibit optical isomerism. So if Cl they are on the same side, it is cis. If they are on the opposite side, it is trans. If we talk about optical isomerism or enantiomerism in octahedral complexes, we can have a complex like MAA whole thrice, but 3 moles of bidentate ligand. So you can see dextro and levo form, non-superimposable mirror image. The another form we can have MAA2X2, that means 2 bidentate ligand and 2 monodentate ligand. So if the like group they are on the same side, like Cl and Cl, it is dextro as well as cis. The another one, the mirror image is also cis but levo. Next we can have MAAX2Y2, that means 1 bidentate ligand. So you can have a non-superimposable mirror image of that also. So with this, we have finished up with the isomerism of coordination compounds. And that all we will end up for this class. In the next class, we'll be doing CFT and IUPAC nomenclature of coordination compound. Thanks for joining. Please do subscribe my channel. Thanks a lot.